Hey there, Green Lemons. We've been talking about how solutions form and how we can affect whether we can make things dissolve more or less or faster or slower. But it's not always quite as black and white. I've told you in the last lesson that like dissolves like. So anything that is like water, which is polar in nature and has a positive and negative end, can dissolve in water, including ionic substances, which are all the way positive and negative. But the reality is there are some ionic salts that just won't dissolve in water. What I'd like to do today is give you guys some clues on how you can figure out which salts will dissolve and which ones won't. On the back of your periodic table and in your notes, you have a list of solubility rules. There's many versions out there, and this is the one that I find the easiest to understand, but they all basically say the same thing. Every once in a while, two different ions, a positive and a negative, attract each other so strongly that the water molecules just can't pull them apart to form cages around them. So there's a list of rules to let us know when are these attractions so strong that they can't be separated, and when are they easy to separate. As we take a look at this list, you'll notice that most of the rules let us know about things that are soluble. Things that are soluble are things that will dissolve in water. And we always indicate this by putting the symbol AQ for aqueous behind a species that we know will dissolve in water. Insoluble talks about things that will not dissolve. Insoluble substances, we often will put the symbol PPT after it, which means precipitate. Or, being chemists, we actually have shorthand for our shorthand. We could put a downward pointing arrow to indicate that there's a precipitate forming, and we'll probably end up in a chunky stuff on the bottom of our test tube. This list of rules lets us know whether or not things will be soluble and will dissolve, or insoluble and will not. Let's take a look at each of them separately. Rule number 1 says all common salts of group 1A elements and ammonium ion are soluble. Group 1A is the alkali metal family. Sodium, potassium, lithium, all the way down the column. Anytime they are part of a compound, it doesn't matter what the negative, the anion half of the compound is. That compound automatically dissolves. They just would rather go hang out with the water than they would stay attached to their anion. Ammonium, which is the NH4 with a +1 charge ion, and you'll find that on your polyatomic ion list, also acts like an alkali metal. As soon as it's part of a compound, if you put it in water, it automatically dissolves every time. Rule 2 says any compound with acetate or nitrate is soluble. Acetate's formula is CH3COO with a -1 charge, and nitrate is the NO3 group with a -1 charge. Just like the above, if we have any compound that contains these ions, it doesn't matter in this case what the cation is. It could be attached to any cation. It doesn't matter. The compound dissolves. I want to point out here that we'll never have half a compound dissolve and the other half won't. You can't dissolve the positive half without the negative half now being freed up to also be surrounded by a cage of water. So if we see any of these compounds, any of these particular ions in a compound, that entire compound will get ripped apart from each other by the water molecules. The water molecules will form cages around the positives and around the negatives, and that compound dissolves. These compounds will dissolve completely. Now, Rule 3 talks about group 7A. This is our halogen family. The halogen family also tends to be very soluble when it's a part of a compound and we put it in water. An exemption to this is fluorine. When fluorine's holding on to a cation, a positive ion, it doesn't let go, so fluoride compounds don't typically dissolve. In this case, we'd mark that as a precipitate. There are 3 other exceptions: silver, mercury, and lead. When silver, mercury, and lead hold on to halogens, they also hold on with a stronger force of attraction than water is capable of overcoming. So if we see a compound that contains fluorine, unless that compound is attached to a group 1 element, it won't dissolve. If we see silver, mercury, or lead attached to any halogen, it won't dissolve. So this is the first time we have an exception to the rule of things being soluble. It's very similar with Rule 4. Rule 4 talks about sulfates. Sulfates also tend to be very soluble in water. The exceptions here is if the sulfate is attached to, again, silver, mercury, lead, but also barium, strontium, calcium. So there are 6 exceptions to the rule of all sulfates are soluble. These first 4 rules tend to talk about how do I know if something will dissolve. Rule 5 talks about things that almost never dissolve, things that are insoluble. And unless we attach any of these compounds to a group 1 exemption, an alkali metal or ammonium, carbonates, hydroxides, oxides, sulfides, phosphates, and chromates will not dissolve in water. They will be insoluble and will form a precipitate. Take a look on page 20 of your workbook, and we have the first practice problem set here. I'm going to go through a few of these with you as examples. Your first step is to do the double displacement reaction and take a look at what products would form. When strontium chloride and ammonium carbonate react, the strontium will now combine with the carbonate to form strontium carbonate, and the ammonium will combine with the chlorine to form ammonium chloride. Do this double displacement reaction for all of the following, and then we'll go and compare these to our solubility rules and determine which are likely to be soluble and which will be insoluble. Let's take a look at the first one. We don't have a rule about strontium. We have a rule saying strontium's an exception, but only if it's attached to sulfate, and it's not. So I have no rule that says all strontiums will always do something. So let's take a look if I have a rule that says all carbonates, and I do. A carbonate is found here in Rule 5. And carbonates are insoluble unless they're attached to group 1 ions. Strontium is found in group 2 in your periodic table, so strontium carbonate will not dissolve in water. It will be a precipitate according to Rule 5. What about ammonium chloride? Well, we do have a rule about ammoniums. As soon as ammonium's there, we know that this is going to be soluble in water. And when a substance is soluble in water, we label it as aqueous. Now, we could have also identified the chlorine. Chlorine is a group 7 element, so Rule 3 also would say that it was soluble. We don't need both halves of the compound to be defined as soluble. As long as we find one of them as being soluble, and there's no exceptions to the rule, that substance will be soluble in water. Let's take a look at the remaining questions here. First, we'll complete the double displacement reactions for each of the questions. Again, we're making new first name, last name combinations. Instead of barium being with chloride, barium will now combine with sulfate. Instead of copper 2 ion being with sulfate, it will now combine with the chloride ion. It doesn't matter which order you list them in. All of these compounds are going to be in the same tube, in the same pot in the reaction. It just matters that you have both of the new compounds listed. Let's now take a look. Will copper 2 chloride dissolve in water? We don't have a rule about coppers, but we do have a rule about chlorides. Solubility Rule 3 says chloride ions will dissolve in water unless they're attached to silver, mercury, lead. Well, there's no exception here. This will be soluble. What about barium sulfate? Again, no rule about all bariums always, but there is barium listed as an exception. Sulfates are always soluble except if combined with barium. Well, here's barium combined with sulfate. So this is an exception to Rule 4. So by Rule 4, we can see that barium sulfate will not dissolve in water. It will form a precipitate. This would be a great place for you to pause the video for just a moment and try to see if you can determine the last 4 compounds. Will these substances dissolve in water and be soluble? We'll record those as aqueous. Or will they be insoluble and we'll record those as precipitates? Pause the video now and try them on your own. How'd you do? I can see potassium nitrate will be soluble. There's 2 really good reasons for this. One, Rule 1 says if you got a group 1 element in there, it's going to dissolve, and automatically we do. I don't even need to look further. But I could have maybe taken a look at the last name, nitrate, and seen that Rule 2 says, hey, if there's a nitrate, going to dissolve. So no matter how you look at it, potassium nitrate will dissolve. What about silver iodide? Well, there's no rule about all silvers always, although it is listed as an exception in a couple of places. But there is a rule about group 7s, the iodides, and they typically dissolve unless attached to silver, mercury, lead. So a silver iodide will not dissolve. It will form a precipitate. This time I use the shorthand of a down arrow for precipitate. Rule 3 is the reason that we can quote for this. Again, for the very last one, we're going to form sodium nitrate and lead hydroxide. The sodium nitrate by rules 1 and 3 will be soluble in water, so we'll mark that as aqueous. Lead hydroxide will not. Hydroxides in Rule 5 say that they are insoluble unless attached to group 1 ions, and lead is not a group 1 ion. It's found under group 4 and acts more like a transition metal. Lead compounds are very rarely soluble unless attached to acetates or nitrates. Lead hydroxide will form a big black precipitate in the bottom of your test tube. I'm hoping that once you've had time to practice a few of these, that you will be able to determine if an ionic salt will form an aqueous solution in water, or if it'll form a precipitate in water because it'll be insoluble. So I'm going to get you to practice the solubility rules on pages 21 and 22, and see if you can determine whether or not the products formed will dissolve or if they will not.